Hi everybody, this is the next in the series of videos on fluid mechanics, where we're discussing now fluid dynamics, fluids that are actually in motion. And one of the biggest things about that is something called the Bernoulli Effect, which has a lot to do with the reason that airplanes fly and how to sort of throw a curveball. To start with, we need to talk about something called volume flow rate or fluid continuity. And that's sort of how a fluid will change as it moves through a different area. So if you look at this example, I've got a pipe with some water flowing through it, and the flow rate here is about 5,000 liters per second. Okay, that's the volume flow rate. That's how much water is going through a second. And as you can see, of course, it's the same because nothing is different. But also note that the speed of the water is 1.6 meters per second everywhere in the pipe. Okay, that's not really any different. But if I squeeze the pipe here in the middle, as I go from an area of about 3 square meters down to an area of about 0.8 square meters, you can see that that volume flow rate has not changed. So one of the most important aspects about volume flow rate right away is that it is a constant value. And QV, a symbol that is often used for volume flow rate, is the product of the cross-sectional area and the speed of the fluid as it's going through. Now, aside from liters per second, the more common unit I tend to use is the cubic meter per second. Again, area representing the cross-sectional area, the opening, and V being the speed of the flow through the pipe. So it's a constant value no matter what I change in terms of that area, that flow rate was the same. Which means that if the volume flow rate is a number at one point, it has to be the same number at another point. So what happens when I do change things like area? Well, again, as we saw, changing the area did not change the volume flow rate. But what it does change is now the velocity. So now the velocity has increased. So here, from about 1.6 meters per second to now something as high as about 6.3 meters per second. So that should make sense. That means if volume flow rate is constant, area and velocity must be inversely proportional to each other. Something that goes hand in hand with volume flow rate is also what is known as the mass flow rate. And that's the amount of mass, literally, of the fluid that is flowing through a particular area at a particular time. Turns out the mass flow rate is also a constant value. Now that's based on the density and what the volume flow rate actually is. Again, here's what this sort of means. These dots represent a mass of water. And as you notice, those dots kind of have to sort of stay very close together. So in order for that to happen, this mass of water, as it's squeezed down, they still have to stay together. The same amount of mass must pass through the pipe all at once. So that's sort of where the mass flow rate kind of comes in. As again, it's going to be a constant based on whatever the volume flow rate is. Okay, so let's look at an example. Here I have a 5 square centimeter pipe that has water flowing through it at 2.5 meters per second. Then narrows to another pipe that is 2 square centimeters in area. I want to know the volume flow rate, the speed of the water in the smaller part of the pipe, and the mass flow rate in the pipe. Okay, so first of all, a couple of quick things we need to do. We want to look at these areas. Now, 5 square centimeters, ideally what we want to do is to, of course, convert that into square meters. So we're sort of in standard units. So that's an area of 5 times 10 to the minus 4 square meters, which means the second area, 2 square centimeters, would be 2 times 10 to the minus 4 square meters. The velocity at location 1 is 2.5 meters per second. So the first part, calculating the volume flow rate. Now we could calculate it in either part of the pipe, but obviously we want to calculate it in section 1 because that is where we know the most information. So an area of 5 times 10 to the minus 4, a velocity of 2.5, is a volume flow rate of 1.25 times 10 to the minus 3 cubic meters per second. Now to get the velocity in the second part of the pipe, there's two ways you could do this. You could say, all right, I already know what the volume flow rate is. It's constant at 1.25 times 10 to the minus 3. And now I can simply set that equal to the area and the velocity in section 2. You can also, if you want to, go back and say, since the volume flow rates are equal, we can set them up in this particular way too. Personally, I actually like the second way. I always like to go back to my givens whenever possible. And that gives me a velocity in the smaller pipe of 6.25 meters per second. And that makes sense. Since the pipe got smaller, the velocity got a lot faster. Finally, getting the mass flow rate, which is simply the density times the volume flow rate. Well, if this is just water, then the density is 1,000 kilograms per cubic meter. A volume flow rate of 1.25 times 10 to the minus 3, which gives a mass flow rate of 1.25 kilograms per second. It's all pretty easy to do. Okay, so how does this all fit into the idea of Bernoulli and Bernoulli's equation and something called the Magnus Effect? Well, let's look at the idea behind how an airplane flies, using something called an airfoil. Now, an airfoil is just a fancy name for a wing. As I showed you before with the water, any sort of mass of fluid has to stay together throughout its motion. It has to be continuous. So if we have air that's flowing over a uniform surface or around it, it will flow, but any part that has to slightly go around it will have to speed up just a little bit in order for those points to always stay together. So when you shape an airfoil, a wing, into the shape it is, the air that's along the bottom of the wing will move along at a pretty standard speed. But any air that encounters the wing has to be able to get over the top of it. Now remember, all of those parts of the air have to stay together at all times. And if we look at the top, we'll call that location 1 and the bottom location 2. The only way that's going to be physically possible is if the air on the top is going much faster than the air on the bottom, just so those points can all stay together. I mean, it's got to travel a longer distance in the same time. How is that possible? Well, that's the really neat part about Bernoulli's effect. The only way for air to move faster is it has to have less resistance acting on it. So what happens is that the pressure on the top suddenly becomes very low, and the pressure on the bottom is now much higher. So the pressure at 1 is now less than the pressure at 2. Now remember, pressure has to do with force. So that means there's a low force on the top and a high force on the bottom. And that creates the effect called lift, which is why an airplane flies. Pretty neat, right? It's just due to the fact that the airspeed is different on the top and the bottom, which makes the pressure different on the top and the bottom. Now, a similar idea goes with a curveball. The key to a curveball is you actually have to make the ball spin in order to make it curve. So if you want to throw a straight fastball, you can't put any spin on it. What happens is when you throw a curveball, as it's sort of showing, you're throwing it in this direction, okay, to the left. That means that all the air is automatically moving to the right. When you spin the curveball, this part of the ball moves against the air, and this part of the ball on the bottom is moving with the air. So again, what that creates is a high velocity down here on the bottom and a low velocity up here on the top. In turn, wherever there's a low velocity, there's a high pressure. And wherever there's a high velocity, there is a low pressure. And that causes the ball to curve in that particular direction. So depending on which way you spin the baseball when you throw it, or soccer ball when you kick it, or anything like that, that will affect which direction it will actually curve. So that spin turns out to be really important in this idea. So what is the physics and equations around the idea of Bernoulli's equation? Well, Bernoulli's equation says this. Pressure plus 1/2 density times velocity squared plus density times gravity times height is a constant value. So again, P standing for pressure. The rho GH has to do with the density and depth of the fluid, as we've talked about before under idea of fluid pressure. And 1/2 rho V squared has to do with, of course, how fast the fluid is actually moving. Now, if you kind of look at rho GH and 1/2 rho V squared, those are very similar to mgh and 1/2 mv squared, kind of relationships to potential and kinetic energies. But what it means is that these have to be constant values for a mass of a fluid. So if you have fluid flowing in one area and you change something in another area, it will alter different things depending on what it is you're changing. So let's look at an example. Here we have a large pipe that's under the ground and has a cross-sectional radius of 10 centimeters at a point 2 meters below the ground. The water then flows through the large section up above the ground into a smaller section that has a smaller cross-sectional radius of 4 centimeters. And the water is flowing at 5 meters per second in the large section. So we want to know how fast it's going to be flowing in the other section and what the pressure is down here. First of all, figuring out what the velocity is going to be as it leaves this section of pipe, which is out here in the air. Well, that's just volume flow rate. The fact that your volume flow rate at one point has to be the same as your volume flow rate at another point. So the way we can set this up is the area times the velocity at location 1 is equal to the area times the velocity at location 2. These are circular areas. Pi r1 squared times its velocity is pi r2 squared times its velocity. Now again, this is one of the reasons I like to set this up. This actually lets me cancel pi out. Whenever I can cancel things, I want to do that. The first radius, 10 centimeters, 0.1 meters, and a speed of 5 meters per second. The second radius, 4 centimeters, 0.04 meters, times a new velocity. Gives a velocity of 31.25 meters per second squared. Obviously a much, much larger velocity. So that's how I can figure out how fast it's going here at location 2. How do I figure out what the pressure is down at location 1? This is where I'm going to bring in Bernoulli's equation. Again, Bernoulli's equation says the pressure at location 1 plus 1/2 rho velocity at location 1 squared plus rho g h at location 1 has to equal the pressure at location 2 plus 1/2 rho velocity at 2 squared plus rho g h at point 2. A couple things I want to decide here. I want to pick a ground level, a sort of 0 point. So what I want to consider is that right here I'm going to call 0 height. Now what that does, since that's at location 1, it allows me to get rid of this whole section here. I don't have to worry about that because that's going to be 0. Secondly, I also need to make sure I know at least one of the pressures. Now, since this exited to the outside air, the pressure at location 2 must be atmospheric pressure, because that's what it's exiting out into. So now I know that value. Substituting in, I have pressure at 1 that I don't know. It's water, which is a density of 1,000. The velocity at location 1 was 5. Again, that height is 0 at location 1. Then at location 2, the pressure there is atmospheric pressure, 1.01 times 10 to the 5th pascals, plus 1/2 density of 1,000. The velocity I found was 31.25, plus now density of 1,000, gravity's 10, and a height of 2 meters. That's my height. So that gives me my pressure plus 12,500 equals 0.01 times 10 to the 5th plus 4.88 times 10 to the 5th plus 20,000, which gives me a pressure of location 1 of 6.22 times 10 to the 5th pascals, or about 622 kilopascals. Now, again, that makes sense because there should be a lot of pressure at the bottom, because this has to both be able to push the water up 2 meters in height and keep it moving along at its speed. So that's going to take a lot of pressure. Plus it has to overcome the atmospheric pressure for the water to literally escape. And that's how Bernoulli's equation basically works. As long as you set up this relationship where you put all parts of Bernoulli's equation for one location at one point of the equal sign and all points on the other side at the other location on the other side, then you can pretty much solve everything out. One of the keys will always be making sure you know what you're going to call your initial beginning heights and final heights, your beginning velocities and final velocities. In other words, setting up sort of points 1 and 2. All right, see you next time.